Okay, hi everyone, my name's Jess and the title of my talk is What Determines the Learned Predictiveness Effect? Separating Cue Outcome Correlation from Choice Relevance. Okay, so we know that there's a dynamic relationship between attention and learning. So we learn more about cues that we attend to, but we also attend more to cues that might be useful for our learning. So this reciprocal relationship is exemplified in the learned predictiveness effect. So Pelley McLaren first reported the learned predictiveness effect using the design that I'm about to go through. So in this task, participants assumed that they were an allergist trying to diagnose which foods were causing allergic reactions in a fictitious patient, Mr. X. So in stage 1 of training, they were presented with these 8 different compound trials. So each of the letters here corresponds to a different food, and outcome 1 and outcome 2 stand for different allergic reactions. And in each of these compounds, there was a perfect predictor and an imperfect predictor. So if we have a look at these AW trials, for example, you can see that A is always paired with outcome 1. So A is a perfect predictor of outcome 1. In contrast, W is paired with both outcome 1 and outcome 2. So W is an imperfect predictor of outcome 1. So in a second stage of training, participants were told that they would now be diagnosing a new patient, so Ms. Y, and they were presented with new compounds and also new outcomes. So Ms. Y was suffering from a different set of allergic reactions, so outcome 3 and 4. And critically in this stage of training, both the previously perfect and previously imperfect predictors are now equally predictive of their respective outcomes. And then the test phase, participants were presented with new compounds consisting of cues that were either perfect predictors in stage 1 or imperfect predictors in stage 1. Now, if participants were able to ignore what they learned in stage 1 training, then they should show equal learning to both sets of cues in stage 2. However, that's not what the Pelley and McLaren found. They found better learning for cues that were previously perfect predictors in stage 1 compared to cues that were previously imperfect predictors in stage 1. So this is the learned predictiveness effect. So we can think of the learned predictiveness effect as a learning bias towards cues that were previously good predictors of outcomes. Okay, so the general behavioural effect that I've just described to you is accompanied by biases in overt attention. So you can see that people look more at cues that were previously predictive in eye tracking. In associative models, learned predictiveness effects are modelled as changes in associability, so the alpha parameter in models like the Rescorla-Wagner model. And a recent review concluded that there was robust evidence for this predictiveness principle. So the basic learned predictiveness effect has been replicated many times. But what we can ask here is, what is it about predictiveness that drives learned predictiveness effects? So here we make the distinction between the relevance of a cue and its correlation with an outcome. So this distinction is best illustrated in nonlinear discrimination, such as the biconditional discrimination. So this is quite a difficult discrimination with 4 different unique cue configurations. And what you might be able to see here is that each of the individual cues, A, B, C, and D, are paired with the outcome, but also paired with no outcome. So each of the individual cues has a low cue outcome correlation. However, they are all relevant to solving the discrimination. So you have to attend to each of the 4 cues in order to solve the biconditional. So there is some evidence for this relevance principle in animals and humans. So cues that are rendered relevant by serving as part of the biconditional discrimination are learnt about better in subsequent phases compared to cues that are not relevant, that do not serve in the biconditional discrimination. However, there is some contradictory evidence as well. But coming back to the learned predictiveness effect, if it is the case that relevance drives associability changes, relevance could provide an alternative explanation for the learned predictiveness effect. And that's because in the typical design, the relevance of the cues and their cue outcome correlation are confounded. So the perfect predictor has the highest cue outcome correlation, but it's also the most relevant cue in the relevant compound. So the aim of this project was to examine the locus of the learned predictiveness effect by separating cue outcome correlation from relevance. Okay, so this is how we did it. So in experiment 1, we had a design with 2 stages of training and a test phase. So in stage 1, we had 8 different compounds. And unlike the typical learn predictiveness design, all of the cues here were imperfect predictors. So if we have a look at these AW trials, so every time, A is presented and paired with outcomes 1 and 2, and W is paired with outcomes 1 and 3. So every cue is presented, is paired with 2 out of the 4 possible outcomes. So every cue is an imperfect predictor. But what we did manipulate between the sets of cues was whether they were choice relevant or choice irrelevant. And we did that by manipulating the outcome choices available on any given trial. So again, if we focus on these AW trials, so the correct outcome is outcome 1 on AW trials. So if participants are presented with a choice between outcomes 1 and 3, what we can see here is that because Apple, A, is paired with outcomes 1 and 2, Apple is choice relevant, or in other words, attending to Apple will allow you to select the correct outcome on 100% of trials. In contrast, W, watermelon for example, is paired with outcomes 1 and outcome 3, and those are the exact outcomes that appear as choices on that trial. So watermelon is not choice relevant, or attending to watermelon will not enable you to select the correct outcome on 100% of trials. So in this way, the light blue set of cues here are choice relevant, and the dark blue set of cues here are choice irrelevant. So in stage 2, participants are given new patient, new compounds, new outcomes. So now we have outcomes 5 and 6, so new allergic reactions. And again, critically, both sets of cues here are equally predictive of their respective outcomes. And here we tested each of the cues individually, and we were specifically interested in what they learned during stage 2. So again, if participants can ignore what they've learned in stage 1, then we should see equal learning for both sets of cues at test. Okay, so in terms of the analysis, so we calculated a learning score for each cue for each participant, and we did this by taking the difference between the ratings for the correct and incorrect stage 2 outcomes. We excluded participants who performed at less than 60% accuracy in the second half of stage 1 training. That left us with this sample size for each of the 2 experiments. And these experiments were run on MTurk, but we've since replicated both sets of results in the lab. Okay, so onto the results. So on the y-axis here, we've got learning scores. So here, higher scores indicate better learning. And we calculated the average learning score for the set of previously relevant and previously irrelevant cues. So the cues that were relevant or irrelevant in stage 1. And what we found was significantly higher learning scores, so better learning for the cues that were previously relevant compared to the cues that were previously irrelevant. So as you can see here, there are some individual differences. So if we plot the difference score, so relevant minus irrelevant learning scores, what you can see here is a small but reliable relevance effect. So a learning bias towards the relevant cues. So to summarize experiment 1, so we found a significant choice relevance effect. So better learning for cues that were previously choice relevant compared to cues that were previously choice irrelevant. And importantly, we found this effect equating the cues for their cue outcome correlation. So at this stage, we can say that choice relevance could explain the learned predictiveness effect entirely, because as I said in the previous designs, choice relevance and cue outcome correlation were confounded. However, what we didn't do in this experiment was manipulate both cue outcome correlation along with relevance. So what happens when we manipulate both factors together? So that's what we looked at in experiment 2. So experiment 2 used a design that was more similar to the typical learn predictiveness design, in that in stage 1 of training, each of the compounds consisted of 1 perfect predictor and 1 imperfect predictor. So if we have a look again at AW trials, so A is a perfect predictor of outcome 1, so every time A appears, outcome 1 is the correct answer, and in comparison, W is paired with both outcome 1 and outcome 2, okay, so that's represented here. So in this experiment, what we did here was to manipulate whether the imperfect predictor, so whether the blue cues here, were choice relevant or choice irrelevant. So the way that we did that was by, again, manipulating the choices available on each trial. So let's assume that on AW trials, you have a choice between outcome 1 and outcome 2. So A is obviously a perfect predictor because it's always paired with outcome 1, so A is choice relevant. In comparison, W is paired with both outcome 1 and outcome 2, so therefore W is not choice relevant. So attending to W doesn't help you make the correct choice. Now, if we compare that situation to if participants were given a choice between outcome 1 and outcome 3, so again, A is a perfect predictor, so it's obviously choice relevant, but here, because W is paired with outcome 1 and outcome 2, but you're given a choice between outcome 1 and outcome 3, watermelon now becomes choice relevant. So attending to W does allow you to make the correct choice on these trials. So in this way, we manipulated whether the cues were equal or unequal in their choice relevance. And we did that between groups. So we have group unequal and group equal. So group unequal, the cues are unequal, not just in cue outcome correlation, but also in their choice relevance. In group equal, the cues still differ in their cue outcome correlation, but this time they're equated in terms of their choice relevance. Okay, so that's stage 1. Stage 2 is the same as experiment 1, so new patient, new compounds, new outcomes. And we tested the cues individually, and we're specifically interested in what they learned in stage 2 of training. Okay, so here are the results. I'll show you the results for group unequal first. So just a reminder, for group unequal, the cues, so the perfect and imperfect cues differ not just in their cue outcome correlation, but also in their choice relevance. So I guess it's not surprising that we found a significant learning bias. So we got higher learning scores for the previously perfect predictors compared to the previously imperfect predictors. But of course, the question of interest is what happens when we equate the cues in terms of their choice relevance? So can we attenuate or reduce the size of the learning bias when the cues have equal choice relevance? And the answer is no. So we have a similar learning bias in group equal, so significantly higher learning scores for the cues that were previously perfect predictors. So this time, if we take the different scores, so perfect minus imperfect learning scores, again, you can see a small but reliable learning bias in each group, but the magnitude of that learning bias appears to be very similar. So the difference was non-significant, and also the Bayes factor was in support of the null. Okay, so to summarize experiment 2, so in group equal, we found a standard learn predictiveness effect, so better learning for the perfect predictors compared to the imperfect predictors. And in group unequal, we found an effect of predictiveness or cue outcome correlation, even when the relevance of the cues was equated. So what this means is that increasing the choice relevance of the imperfect predictor did not attenuate the learning bias towards the perfect predictor. So for whatever reason, the effects don't appear to be additive, or maybe it's the case that when both cue outcome correlation and choice relevance are available as attentional cues, cue outcome correlation is an easier or a stronger cue to use than choice relevance. Okay, so in experiment 1, we found an effect of relevance equating the cues for cue outcome correlation. But in experiment 2, we found an effect of cue outcome correlation equating the cues for choice relevance. So what this means is that both cue outcome correlation and choice relevance were individually sufficient to show a learned predictiveness effect, but neither were necessary. So choice relevance and cue outcome correlation can result in associability changes and subsequent biases in learning. So in terms of our next steps, so we're trying to think of ways in which to model relevance in this task, but also in, say, the biconditional discrimination. And we're also interested in looking at further interactions between these two factors, not just in the learned predictiveness effect, but also in other attentional effects in associative learning. That's it. Thanks.